Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we continue our discussion on the energy conservation and the topic of central force fields. Okay, so we start right away our discussion with an example, that is the problem again, that of a projectile. Okay, so the problem says we have a body which is projected from the surface of moon, okay, and with speed u and any direction. We need to show that the body cannot escape from the moon if u square is less than 2 mg by r square. U is 2 mg by r square, and what we have is, well, 2 mg by r. So we have that m and r are the mass and the radius of the moon. So this is what we have to show, that there is no escape from the surface of the moon if this happens, right? So again, this is a problem of the motion in the presence of gravitational attraction. So we set up the equations of motion. Well, we want to discuss it in the perspective of energy conservation. So let us try to do that. So we know that our central force field here is minus m capital M g over r square. Well, r square, r, small r is any distance, r hat. So this is our central force field. From here we can find what is the potential. See, we want to do this problem using energy consideration. So we first find the potential energy of the system, and we see that V is minus integral f dot dr, right, fdr, and we see that this is when we integrate this system, we find that this is minus m capital M g by r, and what have we got? We have found the potential, scalar potential. So let us write down the energy conservation principle. We see that the total energy, which is the sum of the kinetic energy, this is the speed, minus plus the potential energy. So potential energy is m capital M g by r is going to be a constant, E. But E can be found using the initial condition, which is equal to half m u square minus mg by capital R. So that is the initial setup or the initial energy of the system based on the initial condition, right? And it is kept on the surface of the moon. So hence we have capital R. So now we can find, so my velocity, my speed v mod v square comes out to be u square plus 2 mg times 1 over r minus 1 over capital R. Okay, or let me rewrite this this expression as follows. So this is u square minus 2 mg by r plus 2 mg by r, right? So notice that again let us rename the first term as 1 and the second term as 2. We see that this quantity is greater than 0 and this quantity is less than 0. the first quantity is always greater than 0. Why? Because we have mass, which is a positive quantity, capital G is a universal constant positive quantity, R is a distance, distances are always positive, so the first quantity is always positive. Now we will have the escape velocity of the moon goes to 0 or less than 0. We want that, what we want? We want that V is negative, so that the projectile, when thrown from the surface of the moon, comes back, that is with the opposite speed, right? We want speed to be in the the velocity to be in the direction opposite to the direction which is thrown, right? Not vertical, but vertically down, for example. So for that, we the first term is always positive, if and only if the second term is always positive. If and only if the first term is negative, then only we can expect that there will be no escape from the surface of the moon. Otherwise, if the first term is also non-negative, it is positive, then we will always have in this particular scenario, we will always have that V is non-negative and there will be escape, right? So that is what we don't want. So we want that V becomes negative eventually, or from this condition 1, we have that U square is less than 2 mg by R. Okay, so our condition comes out. Okay, so let us now look at another example. So this problem says a particle of mass m can move under gravity. The particle of mass m can move under gravity of two particles of equal mass, let's say capital M, under the these are all fixed at 0 0 plus minus a, right? We need to show that the origin O is an unstable equilibrium. Okay, particle of mass m can move under gravity of two particles. So we have two particles which are sitting at two ends and they are fixed at let's say minus a, 0 0 minus a, and this one, the second, is at 0 0 plus a. So now we have a particle of mass m which is moving under gravity here. So it is going to move along the lines of the point along the line of interaction. So we expect that if the particle is at a distance a minus z here, it will be at a distance a plus z here. So we can write z or x, but so we can write the equation of motion. We don't want to do that, we want to write the potential. But to do that, let us write the force due to the gravitational attraction. So we have that the potential, you can directly write the potential. We have already seen in the previous example, the potential can be written down from the force, gravitational force. The potential V at 0 0 z at any given point where this mass small m is going to be minus m capital M G, one with position a minus z and the other with position a plus z, and we see that this is equal to minus 2 am capital Mg divided by a square minus z square, right? And we see that this is going to have a maxima at z is equal to 0, right? So we expect So this is going to have a maxima, well, but we have a minus sign. So the potential will have a minima. We'll have a minima at z is equal to 0, and we see that, hold on, I think something is missing. Let me take this statement back again. We see that the potential V00z has a maxima at z is equal to 0, right? We can check that, and which means that since 0 z is equal to 0 is a point of maxima, we conclude that the potential V00z at z is equal to 0 is a point. So, well, we conclude the following, that the point z is equal to 0 is an unstable equilibrium. Unstable equilibrium. Okay. So whenever we have a minima of the potential, stable equilibrium, maxima of a potential, unstable equilibrium. Okay, so then we come to a class of motion where the particle is moving under some constraints. This question arises, what is the work done by the constraints on the particle? Okay, so what are we going to see next? We are talking about energy conservation in a constrained motion. So what am I saying here? For example, we saw that pulley, the pulley string system, where the masses were moving along the pulley and they were attached to a string, right? So this is a case of a constrained motion. So this is a case of a constrained motion where the particles are getting, they are moving under the action of the tension due in the string. So the pulley mass system is a constrained motion. Similarly, if we look at the particle which is sliding along an inclined wedge, then the particle motion is also constrained motion, because it is constrained to remain on that inclined wedge due to the action of the normal reaction of the wedge, right? And then there are lots of other such motions. These are some of the common examples that we have seen in the previous modules. So this question is, what is the work done by the constraints? It turns out that constrained forces arise because of the way the particle is moving in a typical setup, and this is not something that is due to the natural motion of the particle, or the constrained forces do not arise naturally by some external agent, right? So it turns out that the constrained forces do no additional work. So that is an important point. So the constrained forces do not work. There is no work done by the constrained forces, right? So no work done. For example, again we can go back to the string pulley system. It turns out that the tension in the string does no work. Similarly we have the reaction forces. On the edge does no work on the particle which is sliding to the ground, right? So what we have is that the energy conservation tells us, we can conclude all this discussion in the form of an energy conservation principle, which says that the energy conservation principle says that the kinetic energy, the sum of the kinetic energy and the potential energy of the particle under constrained motion remains constant. Since the constrained motion is not not contributing to any additional work done on the system, we again expect the energy conservation to hold true for a conservative field under constrained motion. Okay, so let me rewrite the energy conservation principle for constrained motion. Okay, so it says the following: the sum of the kinetic energy plus the potential energy of a particle subject to constraint in a conservative force field remains constant. Okay, the kinetic plus potential energy of a particle subject to the constraint of a conservative force field remains constant. Okay, so we have actually added a bit more information in the energy conservation principle. So let us look at an example, a very interesting example of a particle moving in a constrained hoop. So what have we got? So the problem says we have a fixed hollow sphere. We have a fixed hollow sphere which has a center O and a smooth inner surface of radius b. So we have this sphere where the center of the sphere is O and the radius of the sphere is b, right? And then the problem says a particle P which is inside the sphere is projected horizontally with speed u, and then from the lowest interior point, and we need to show that v square, the speed at any given point, is going to be u square minus 2gb 1 minus cos theta. Okay, such that the particle P remains in contact with the sphere. Okay, so what have we got here is we have a sphere, and let me try to draw this diagram a bit more carefully. We have a sphere, and inside the sphere we have a particle of mass m, and the radius of the sphere is b, and along we expect the mass to be in the downward direction, and then we have that the speed of the sphere is at t equal to 0, the sphere is getting projected with a horizontal velocity speed u at the lowest point, and at any given point it is subtending an angle theta. So now we can complete the force, we can complete the force diagram or the force picture. So this is theta as well, and we see that this is going to be mg cos theta, and we expect that this is going to be mg sin theta, right? And we expect that we have the acceleration v is, the velocity v is b times theta dot, and we will also have a normal reaction which is acting along the radial direction centrally, right? So we expect that, so from energy we can directly use energy conservation. So from energy conservation principle, remember we need the particle to be on the surface of the sphere at all times. So that is a constrained motion of the particle on the surface of the sphere. So under this constraint we have this energy conservation principle, that half the total kinetic energy half mv square minus the total potential energy. So the total potential energy is going to be will be what? We have mg so mg minus mg b cos theta. So here we have so the total potential energy is at a distance. So we have this distance b. So or this is also distance b. So mg b cos theta. So b cos theta is this distance that we are drawing. So this is my b cos theta. So mgb cos theta is the potential energy at any given point subtending an angle theta, and this is also equal to the total energy, which is can be calculated at the value initially. This is going to be half mu square minus mgb. This is the value originally at the bottom of the sphere, and we see that this is also equal to v square minus 2gb cos theta is u square minus 2gb. Okay. So from here we can quickly find what is the velocity. The velocity is such that v square is u square minus 2gb 1 minus cos theta. Okay. 1 minus cos theta. Okay. So that completes the first part of the problem. We can also find what is the normal reaction force. So the normal reaction force is so n minus mg cos theta, that is the net force acting along the radial direction, has to be equal to the radial acceleration mv square by b, right? And we can plug in this this formula for v square, and we get that this is also equal. We get that the reaction forces come out to be mu square by b plus mg cos theta 3 cos theta minus 2, right? So that is my normal reaction forces. Okay, so then the next part of the problem says that what have we got? The next part of the problem says that if my initial projected speed is this quantity square root 3 gb, if, then we have to show that we show that p is going to leave will leave the surface of sphere and we need to find the value of theta. We need to find the value of theta at which it does. Right? So what have we got here? So we see that when we have u square is 3 gb, that is what is given, right? We can quickly find what is my velocity. So my velocity was with this formula was the following. So I can plug in the value of u in this formula, and I see that my velocity v square comes out to be gb 1 plus 2 cos theta, right? So it turns out that in this motion, the particle is going to go all the way up to a point, all the way to a value of theta such that the velocity is 0, right? So the velocity v equal to 0 is a point, let's say the point p star or p prime. This is the point at which the particle is going to stop and it is going to start to go down or go in the other direction. So it turns out that at the highest point we need to have v is equal to 0, or that happens when cos theta is minus 1/2, right? We set this equal to 0, or we get that theta is 120 degrees 2 pi by 3, and we expect that the particle is going to oscillate, the particle oscillates from theta from minus 120 degrees to plus 120 degrees, right? Will that ever be true? The problem is not, because we will show in a moment that within this range the particle is not going to stay put on the circle or on the sphere. It is going to take off, or it is going to go up, or it is going to go away from the surface of the sphere, right? Now notice what is the normal reaction. The normal reaction that we had found for u square is equal to 3gb, the normal reaction comes out to be mg 1 plus 3 cos theta, and the normal reaction will be 0 when cos theta is minus 1/3 or theta is 109 degrees. So which means at 109 degree the normal reaction is 0, and after theta is greater than 109 degrees, then we have a negative normal reaction. That cannot happen, and that is only going to result in the fact that the particle is going to go away from the surface of the sphere. So the particle will leave the surface inside this range from minus 2 pi by 3 to plus 2 pi by 3. Okay. We can quickly find that at theta equal to 109, or cos theta is minus 1 by 3, we can find what is v, the velocity of the particle, because the particle has not stopped at this angle, right? It stops at this angle 120 degrees. So at 109 the velocity comes out to be, we plug this in the formula for v comes out to be square root gb by 3, right, when u square is 3gb. Okay, so then the third part of the problem says is how large should you be such that P performs complete circle. Yeah, right? Circle. Okay. So for complete circle, I have that we must be, so we need to have that theta. So for complete circle, theta max could be 180 degrees. So if theta is going from plus pi to minus pi, then the system is performing complete circles, right? So for that case, we also must have that v has to be positive and non-negative, and n also has to be non-negative, right? So when we plug in the formula for v, we can quickly see that we get the inequality u square has to be greater than 2gb 1 minus cos theta, and from the normal reaction expression we get that u square is greater than gb 2 minus 3 cos theta, right? And at theta equal to 180 degrees, we can find that u square, the first inequality is going to give u square is greater than 4gb, the second gives us u square is greater than equal to 5gb, and when we satisfy the second inequality, u square greater than equal to 5gb, then the first inequality is automatically satisfied. So the answer lies that u has to be at least equal to 5 gb square root, so that the particle goes from minus 180 degrees to plus 180 degrees. So let us now wrap up our discussion in this topic, and just want to remind that in the next topic we are going to talk about the orbital motion of the satellites in this central force field. So we will go deeper into this area of gravitational force field and show some interesting results. So thank you so far for listening.